Greetings to everyone. Our topic today will focus on Chapter 2, Speaking Mathematically, which include the following topic of variables, language of set, and lastly, language of relation and function. So, without further ado, I will now start. Do you have any idea about the variables and usage? If not, variables in mathematics, a symbol which work as a placeholder for expression are quantities that may vary or change. Is often used to represent the argument of a function or an arbitrary element of a set. In addition to numbers, variables are commonly used to represent by vectors, matrices, and functions. So this is the representation of variable in math. In algebra, a symbol, usually a letter, standing in for an unknown numerical value in an equations. In translating word problems into algebraic equations, quantities to be determined can be represented by variables. So, this is the example of variables in mathematics. In math, variable is an alphabet or term that represents an unknown number or an unknown value or an unknown quantity. That variables are commonly used in the case of algebraic expression on algebra. So this is the example. X plus 9 is equal to 4 is a linear equation where x is a variable, where 9 and 4 are constant.
Advantages of variables allows us to give temporary name to what you are seeking so that you can perform concrete computation with it to help discover its possible values. Variables and constants in algebraic expressions. Two types of variable in statistics. Dependent variable. The dependent variable is characterized as the variable whose quality depends on the estimation of another variable in its condition. That is, the estimation of the word variable is dependably said to be found on the free variable of math condition. Independent variables. In an algebraic equation, as an independent variable describes a value whose values are independent of changes. If x and y are two variables, is an algebraic equation, and every value of x linked with any other value of y, then y value is said to be a function as an independent variable, and y value is known as an independent variable. When we say independent variable, it is the input value where the value is given or within the equation. For example, x is equals to y plus 5 and y is equals to 7. Then the input value is 7. Otherwise, the dependent variable is the output value or the equivalent value of the input value. And the given number is in every equation which will give us the value of x. In the given equation where x is equals to y plus 5 and y is equals to 7, when x is equals to 12, which the output value of the given variables.
To explain and understand more about variables, here are the three kinds of mathematical statement. First, universal statement. It is translated as for all, give any, for each, and for every. It means that it is applied in general and that a certain property is true for all objects of a given type. While conditional statement is represented by if-then. It means that the word if is inseparable to the word then, and whenever the hypothesis which is true, therefore the conclusion is also true. Lastly, existential statement is translated as and means variously for some, there exists, there is a, or for at least one. It expresses the existence of at least one object which has a particular property. For example, a prime number exists and that prime number also possesses or is also an even number.
The language of sets.
George Cantor, 1845 to 1918, introduced the word set as a formal mathematical term in 1978, simply as collection of elements. Sets. A set is a well-defined collection of distinct objects. The elements that make up a set can be any kind of mathematical objects, numbers, symbols, point space, line, other geometrical shapes, variables, or even other sets. It can be represented by listing its elements in a set are specifically listed. Example: A is equal to the set of A, E, I, O, U. B is equal to all set of plane figures.
Notation. Notation uses symbols or symbolic expressions that are intended to have a precise semantic meaning. A mathematical notation is a writing system used for recording the concepts in mathematics. In the history of mathematics, these symbols have denoted numbers, shapes, patterns, and change. Using the set roster notation, these are the example. Let A denotes the set whose elements are 1, 2, and 3, and B denotes the set whose elements are 3, 1, and 2, and C denotes the set whose elements are 1, 1, 2, 3, 3, and 3. What are the elements of A, B, and C? How are A, B, and C related? A, B, C have exactly the same three elements, 1, 2, 3. Therefore, A, B, and C are simply represented in different ways. If the set has a symbols of dots, the dots called ellipses, and read as, and so forth.
Example number 2 is braces 0 is 0. 0 is not equal 0 because braces 0 is a set with one element, namely 0, whereas 0 is just a symbol that represents the number of 0. Set of numbers are frequently referred to that they given special symbolic names. Symbol N, W, C, Q, R, Z, Q. Set N is set of natural numbers. W is set of whole numbers. C is set of complex numbers. Q set of irrational numbers. R is set of all real integers. Z is set of all integers. Q is set of all rational numbers or quotation of integers. The number 0 corresponds to a middle point called the origin, and it is neither positive nor negative. A unit of distance is marked off, and each point of the right of the origin corresponds to a positive real number found by computing its distance from the origin. Each point to the left of the origin corresponds to a negative real number, which is denoted by computing each distance from the origin and putting a minus sign in front of the resulting number. The set of real numbers is therefore divided into three parts: the set of positive real numbers, the set of negative real numbers, and the number 0. Example: positive numbers include the natural or counting numbers like 1, 2, 3, 4, 5, as well as fractions like 3 over 5 or 232 over 345, and decimals like 44.3.
Set builder notation. In set theory, in its application to logic, mathematics and computer science. Set builder notation is a mathematical notation for describing a set by enumerating its element or stating the properties that its member must satisfy. X is an element of S such that P of X. Example: Z the set of all the positive integers. X is an element of the set of all positive integers such that negative 2 is less than X and X is less than 5. Another one. Since all the integers in Z are positive, X is an element of the set of all positive integers such that negative 2 is less than X and X is less than 5 equals 1, 2, 3, 4.
Subsets. So, what is subset? A subset is a set whose elements are all members of another set. It is a basic relation between sets. There are two representational symbols of a subset. One, which is like a sideways U with a bar underneath, that means is a subset of, and then a symbol that looks like a sideways U without a bar, that means is a proper subset of. So let's be more specific. Let's say if A and B are sets, then A is called a subset of B. This is written symbolically as A is a subset of B if and only if every element of A is also an element of B. Now, if set B does not have any similar elements from set A, basing on the definition, set B is not a subset of A. Because we can only consider a set as a subset of another set only if they have the same elements as the other. We also have this called empty set or null or void set, which means the unique set having no elements. Its size or cardinality or count of elements is a set is 0. Here is an example of a subsets. We have these whole numbers 0, 1, 2, 3, 4, 5, and 6, and 7. Let's use our subset as the elements of 1, 2, and 3. Same goes to our set B. And our set C would be 5, 6, and 7. And set D contains the elements of 0, 1, 2, 3, 4, and 5. Since all of the members of set A are members of set D, A is a subset of D. Symbolically, this is represented as A as a subset of D. A is also a proper subset of D since set D has members that do not belong to set A. A is a proper subset of D implies that the numbers of set A is less than the numbers of set D. Since some of the members of set C are not members of set D, C is not a subset of D. And since all of the members of set A are members of set B, A is a subset of B. Although A is a subset of B, since there are no members of set B that are not members of set A is not a proper subset of B. Let's note that any set is considered to be a subset of itself. No set is a proper subset of itself. The empty set is a subset of every set. And the empty set is a proper subset of every set except for the empty set.
About the proper subset, let A and B be sets. A is a proper subset of B if and only if every element of B is in A, but there is at least one element of B that is not in A. Example, A 1, 2, 3, 4 is a proper subset of B 1, 2, 3, 4, and 5. A proper subset can be represented as A is a proper subset of B. Proper subset is a special case of a subset. A subset is a proper subset if there is at least one element found in the original set that is included in the subset. Pero kapag kompleto at parehong-pareho ang given set, then it's not a proper subset. The symbol of proper subset looks like a sideways U without the line below.
Cartesian product. In 1914, crucial breakdowns were made by Norbert Wiener and Felix Hausdorff, which both give a definition showing that ordered pair can be defined as a certain type of set, but both definitions were somewhat awkward. In 1921, Karamizer and Koratowski published the following definition, which has since become a standard. It says that an ordered pair is a set of A and B, and this is the symbolically given set A and B. The Gaussian product is A and B. We noted A times B and red. Across B is the set of all ordered pairs AB, where A is an A, B is an B. This is the symbolically. Examples. Let's A is equals to 1, 2, 3 and B is equals to UV. Find A times B, B times A, and B times B. A times B is equals to 1U, 2U, BU, 1V, 2V, and 3V. B times A, U1, U2, U3, V1, V2, V3. B times B, U, U, UV, VU, and VV.
Ordered pair. Ordered pair is the usual rotation for ordered pairs refers to A and B. Given elements and B, the symbol denotes. The ordered pair consisting of A and B together with the specification that A is the first element of the pair and B is the second element. Two ordered pair A and B and C and D are equal, and only if A equals C, B equal D. Symbolically, A equal B equals C and D means that A equals C and B equal D.
So this topic is all about the language of relation and functions. So what is relation and functions? Relation. A relation is a set of ordered pairs of x and y. The domain of a relation is the set of first coordinates, and the range is the set of second coordinates. Function. A function is a relation in which elements of the domain corresponds to exactly one element of the range. Therefore, the x value should not be repeated. For example, determine if the relation 1 and 2, 2 and 5, 3 and 10 is a function. The answer is, the relation is a function because the x values are not repeated.
Here are other ways in determining functions. The first one is the mapping diagrams. It is a flowchart for a function showing the input and output values. It shows how elements are paired. Given the example, it shows that the relation is a function. It explains that the x values of 3 and -4 has the same output of 2, and the x value of 5 has the only output of 3. The concept of x values having the same y value or output is called many-to-one. Second is the vertical line test. A graph represents a function if and only if no vertical line intersects the graph in more than one point. The first example on the left is a function as the line on its graph intersect only in one point. On the other hand, the second example is not a function as it intersects in more than one point. And lastly, table of values. A table of values is a list of numbers that are used to substitute one variable, such as within an equation of a line, and other functions to find the value of the other variable or missing number. In this example, the x in the equation was substituted by the indicated x values in the table to find its y value or its output and complete the table of values.
The two types of functions. First is the linear function, and second is the quadratic function. Linear function. A function f is a linear function if f open parenthesis x close parenthesis equals mx plus b, where m and b are real numbers, and m and fx are not both equal to 0. Example: y equals 2x plus 1 is a linear equation. When x increases, y increases twice as fast, so we need 2x. When x is 0, y is already 1, so plus 1 is also needed, and so y equals 2x plus 1. There are some example values that are placed in the PPT or video presentation. Let's just look at the example that is placed so that we can understand, study, and learn from the linear equation that I discussed. Quadratic function. A quadratic function is any equation of the form f open parenthesis x close parenthesis equals ax squared plus bx plus c, where a, b, and c are real numbers and a not equal to 0. Few examples of quadratic functions are in our presentation. Kindly read and know the solutions on how to tackle the problem in this quadratic equation. Examples that we gave.
Constant function. When we say constant function, is a function that has the same output value no matter what your input value is. Constant function. A linear function, f is a constant function if f of x equals mx plus b, where m equals 0 and b is any real number. Thus, f of x equals b. Example: y equals 7. No matter what x value or input is, y is always 7. If x equals 3, y equals 7. Or if x equals 5, y equals 7. Y is always 7, no matter what input is. Therefore, we can get different outputs by varying inputs, and that means this is the constant function. Identity function. When we say identity function, is a function where each element is a set B, gives the image of itself as the same element. Identity function. A linear function. F is an identity function if f of x equals mx plus b, where m equals 1 and b equals 0. Thus, f of x equals x. Okay, example. F equals 1:1, 2:2, 3:3, 4:4, 5:5. We can see that